All right, we are live. Let me copy this for you guys. Now. All right. We are good to go. All right. I set up the link to start you at the beginning, so you might be able to skip ahead. All right, let's get started. Total inductance of several inductors connected in series is calculated the same way as total resistance of several resistors connected in. So, inductance, total inductance, and total inductive reactance is calculated exactly the same way as resistance. So, inductors and resistors calculate exactly the same way. They don't calculate together the same way. That's what AC Theory Level 2 is about, is mixing resistors and inductors and resistors and capacitors and all of that. But for now, just inductors by themselves calculate just like resistors by themselves. Or, you know what I mean. A circuit with only inductance, everything calculates the same way as a circuit with only resistance. Alright. So inductors in series calculates the same as resistance in series. Inductance in parallel calculates the same way as resistance in parallel. So yeah, that's what I just said. Total inductance and total inductive reactance cannot be calculated the same way. So what this question is saying is, if you have a bunch of inductors and you know all of their inductive reactances, you can calculate their total. You can total them up the same way. So you can take all the let's see, the Henries. Inductors are measured in Henries. So you can take, let's just grab, make a new one. Don't save. Okay. Don't save. Okay. So you could have a circuit. Let's just make it simple. We're not going to use a battery. We're going to use a voltage source. Five Henries and 10 Henries. And let's say this has X of L is, so that's inductive reactance. Inductive reactance. And let's say that was 50 ohms and it was double, so let's say X of L here is 100 ohms. To get L total, you just take L1 plus L2. To get X of L total, you take X of L1 plus X of L2. That's it. It's exactly the same. Capacitors are where things are different. Inductance will have no effect in the DC circuit as long as current is constant. Inductors, which are like transformers or electromagnets, they don't do anything as long as... Oh, I'm so sorry for that sound. If that came through. They don't do anything as long as current is constant. They oppose a change in current. So they will be active if current is changing, but they don't do anything. Current stays the same. Okay, this is just a joke answer. Yes, it is represented in mathematical formulas as the Greek letter delta, which is a triangle. Is not delta triangle. No. I think that's the pound symbol. No, that's like the euro symbol. What is the unit for inductance? Henries. Inductors are measured in Henries. Dead simple. Inductive reactance. Ohms. Inductive reactance is measured in ohms. All reactance is measured in ohms. How many time constants will it take for an inductor to reach full current? 5. It takes 5 time constants. Hopefully y'all have your AC theory book and you're using it. Yes. It's counter electromotive force because it's 180 degrees out of phase with the applied voltage. So it's flowing against. It's not flowing, but it's pushing against the normal current. What percentage of maximum is the first time constant? 63.2% of maximum. When adding additional inductors to a parallel circuit with existing inductors, the total inductive reactance of the circuit will decrease. Yes, so just like one of the first questions we did today, if you add additional resistors to a parallel circuit, total resistance goes down. Same thing with inductive reactance in parallel. That is the definition of inductance. There's no reason to have missed this question. You've got a book. You've got Google. But yes, this is just straight up the definition of inductance. Whenever current flows through a conductor, a magnetic field is created around that conductor, or in the conductor. Yeah, you can see that, if you like, or that's how a no contact voltage tester works. It picks up the magnetic field around a conductor. Also, if you look at a clamp-on voltmeter or current ammeter, a clamp-on ammeter, that's how they work. Is they read the intensity of the magnetic field around a wire. All right, Lenz's law. Well, I think we're only halfway through. I'll pick up the pace. I should have done this separately. Maybe we'll end early. Because I'll probably split this tomorrow. Lenz's law states that the induced voltage or current blanks the motion that induced the voltage or current. Yes. You can see that. I think I played this video in class where the guy takes a magnet and swings it towards some copper, and it stops the copper, or stops the magnet. Oh, that's not the right button. Yes. This is the quiz that we did in class. I'm gonna skip some of this stuff. Inductors always oppose a change in current. Let's see. Yeah, this is not going to carry over. Capacitance is measured in farads. Okay, here's where we're back to the important stuff. Capacitance is measured in farads, and that is sorry, just got a haircut and my neckline is itching. It has to do with George Faraday. Capacitive reactance is measured in ohms. Capacitance, everything, all the calculations for capacitance are inverted from all the calculations for resistance. Capacitive reactance is exactly the same. So capacitance is the only thing that's different out of all of this. And it's just capacitance in series calculates like resistance in parallel. And capacitance in parallel calculates just like resistance in series. But we'll see some formulas, see some calculations based on that. What type of current is effectively passed by a capacitor? AC current is effectively passed. So the way a capacitor works is it's like there's two chambers in the capacitor, and there's a separation between them, and it fills up. There's like a rubber barrier or like a barrier in between them that's flexible. As you start filling from one side, it inflates and pushes, and whenever it gets full, it stops the current flow. And then whenever you start discharging it, current flow starts again until it fills up the other side, and then it stops. With AC, the direction of current flow is constantly changing. So it's constantly charging and discharging and charging and discharging, and it doesn't ever hit that maximum charge. That's also why the faster your frequency, the higher your frequency, the lower the opposition of the change of voltage it provides. Because just like a balloon, as you inflate a balloon, it gets harder and harder to inflate the more you inflate the balloon. A capacitor is the same way. It starts getting harder and harder to charge the capacitor the higher the charge goes. So if you're never hitting that maximum, like the hard stop, if you're only playing in like the 50% range, because as soon as it hits 50%, it's discharging and going to the negative 50% range, and it's constantly going back and forth, it's going to be a lot easier. It's going to provide a whole lot less opposition of the flow of currents. Okay. Capacitance is the ability of a circuit component to store an electrical charge. A capacitor is a lot like a battery. There are some cars that I saw something about race cars a while back that they are using supercapacitors instead of a battery, because the capacitors are so much lighter than a car battery, and it saves them that, you know, the weight of the battery by just having the capacitor. But it's not great because capacitors do discharge while they're sitting. But if you're just gonna jump the car off and drive, you know, 500 miles in a circle, you don't really care about, okay, well, if I park it, it's gonna not start next time unless I jump it off. You can just charge the capacitor up, crank the car, and go. Total capacitance in series. So this is total capacitance in series is calculated the same as total resistance in parallel. Discharge the capacitor after the circuit is turned off. 5 time constants is always 5 time constants, no matter. I mean, I guess that there will be situations, but not in this class. It's always 5 time constants. If you're ever asked, it's going to be 5 time constants. But that's stuff for the last test. How to calculate a time constant, we don't care about that. In a purely capacitive circuit, I pretty much covered this, but in case somebody's skipping around looking specifically for this question, current can only flow during the time the capacitor is charging or discharging. So capacitors, they inflate and deflate, and they have a maximum amount that they can inflate. They don't literally inflate. That's just a metaphor. But they inflate and deflate, and current can only flow while they're inflating or deflating. A non-polarized capacitor. There are some DC capacitors, because capacitors can operate in a DC circuit, but they will block current flow whenever they get fully charged. So they have a completely different use in a DC circuit versus an AC circuit. Yes. Inductors oppose a change in current, while capacitors oppose a change in voltage. Alright. We're just about right on time. Wow, lots of people didn't do this one. It is rough to get to this one while you're running back and forth. Let's find... We're not in first year, we're in second year. AC theory... I think we want to do all the math now. Yeah, we're going to do all the math. Alright, and let's get started in here. Alright, I'll see you guys in a couple hours.